Chapter 17, Power and Sample Sizes. Section 17.1, What is statistical power? Here are a few equivalent definitions of statistical power. The probability that you will not commit a type 2 error. The probability of rejecting the null hypothesis when the null hypothesis is actually false. The area of the theoretical alternative distribution that is more extreme than the alpha threshold, which is also referred to as 1 minus beta. I will expand on this definition in the next section. The probability of finding an effect when there really is an effect to find. An arbitrary number that you don't really understand yet need to maximize when writing research grant proposals and ethics applications. Statistical power is expressed as a number that ranges from 0 to 1, with larger values corresponding to higher power. There is no specific cutoff for enough statistical power, but values above 0.8 are generally considered an acceptable minimum. The interpretation is that if the power is 0.8, then there is an 80% chance that you will not get a type 2 error. And remember that a type 2 error is not rejecting the H0 when it is actually false. The analytical formulas for computing statistical power rely on the population mean and population standard deviation, but these quantities are usually unknown. Therefore, in practice, statistical power is estimated based on sample means, sample standard deviations, and sample sizes. For this reason, one of the most common applications of statistical power is to estimate an appropriate sample size before the research begins. That is, before you start data acquisition, you would perform a power analysis to determine the amount of data that is likely to be sufficient for statistical analyses. In the first part of this chapter, you will learn about interpreting and estimating statistical power, and then you'll learn how to invert the power calculation to estimate an appropriate sample size for a given analysis and level of statistical power. Section 17.1.1, Statistical Power in a Graph. Figure 17.1 shows the graphical representation of statistical decisions based on H0 and HA distributions as discussed in Chapter 10. This paragraph references Figure 17.1, which highlights two things. One, we have a table on the left that shows the 4 possible statistical decisions, where the columns are titled Reality about H0, with the 2 columns being titled H0 is true and H0 is false, and the rows correspond to the decision. The 2 options there are don't reject H0 and reject H0. This is a table that I have described in a previous chapter, in Chapter 10, about hypothesis testing. All of the labels, so true negative, false negative, and false positive, are grayed out, and the only thing that we can really read clearly is true positive, which is also 1 minus beta, and that is the cell corresponding to where the reality is that H0 is false, and the decision is to reject H0. Okay, that's the left side of the figure. Then we have a diagram on the right that shows that statistical power is the area to the right of the chosen alpha level. Now, what we see here is 2 Gaussian distributions that are shifted from each other. We have the H0 distribution on the left, and the HA, the alternative hypothesis test statistic distribution, on the right. The x-axis is labeled test statistic value. There is a vertical gray dashed line labeled alpha that captures just the rightmost tail of the H0 distribution, but it actually contains the bulk of the HA distribution because that one is shifted to the right. The area to the right of the alpha line in the HA distribution is shaded in dark gray, and that area is labeled 1 minus beta. Back to the text. This diagram illustrates several important points about statistical power that I will mention here and provide more detail about throughout the chapter. Point 1. Statistical power is the area of the HA PDF that is more extreme than the chosen alpha level, also called 1 minus beta. Point 2. The statistical power is dependent on the distances between the two distributions and on their widths, which is often a function of the sample size. Point 3. This figure shows a one-tailed power calculation. In most cases, the total statistical power is the sum of the area to the right of alpha over 2 and to the left of minus alpha over 2. Point 4. The HA distribution is based on assumptions about a hypothetical distribution of test statistic values and is modeled as a shifted version of the H0 distribution. Point 5. In reality, you do not have an HA distribution. You have one value of the test statistic. So the HA distribution depicted here is derived from a formula and is based on assumptions, just like the H0 distribution is. Point 6. That said, it is possible to estimate this distribution using computational techniques, although it is still based on assumptions and therefore may be inaccurate. I'll explain this towards the end of the exercises. Why is the definition of power, quote, rejecting the null hypothesis when the null hypothesis is false, end quote? Wouldn't it be simpler to say, identify a real effect? Yes, that is temptingly simple, and people do colloquially speak of statistical power in this way. Indeed, I wrote this as one of the definitions of power at the outset of this chapter. But rejecting H0 is not the same thing as HA being true. As you know from chapter 10, it is not possible to prove an hypothesis using inferential statistics. Instead, we can only say that there is sufficient evidence to reject the null hypothesis in favor of some other hypothesis that is better than H0, but not necessarily true. Therefore, defining statistical power as rejecting the null hypothesis when it should be rejected is more conservative and appropriate. Section 17.1.2, How much power is enough? As with all statistical thresholds, the threshold for having quote-unquote enough power is inherently arbitrary and subjective. 0.8 is a common acceptable minimum in many fields in the biological and social sciences. A minimum of 0.9 is used in research where reproducibility is the primary goal. In medicine, the power levels are often 0.9 or 0.95. This is justifiable. Research that has direct implications for human health and safety should meet higher statistical standards compared to curiosity-driven or market research. It may sound strange to accept lower levels of power. Why not ensure that all research has a power of 0.99? Indeed, if the effect is really out there in the real world, shouldn't we be able to find it with our experiments and statistics? Unfortunately, it's not quite that simple. You might have a small sample size and high variability. Perhaps you are testing a finding with a small expected effect size. There are practical considerations that limit the amount of data researchers can collect, and there's no guarantee that nature works the way you think it does. That is, you cannot expect to reject the null hypothesis simply because you want your hypothesis to be confirmed. Furthermore, there might be ethical issues with collecting arbitrarily large sample sizes if participating in a study could have negative consequences. Think of side effects of medications or surgeries, financial burdens, ethical considerations in non-human animals, or psychological or emotional demands on human research participants. Thus, there is a myriad of reasons why sample sizes should be big enough but not bigger than they need to be. Many aspects of statistics seem obvious or easy when they're written out in a textbook, but reality hits like throwing a cotton ball against a brick wall. Section 17.2, Estimating Statistical Power. This section is titled Estimating and not Calculating for a reason. Statistical power can be exactly calculated only if you know the population mean and the population variance. In practice, you don't know either of these, but you can only estimate them through the sample mean and sample variance. Therefore, statistical power can only be estimated. Furthermore, Figure 17.1 shows a distribution of HA values, but in practice, you do not have such a distribution. You have only one test statistic value that you compute from your sample. This means that sample power cannot be computed directly. It can only be estimated based on assumptions and formulas. But wait, it gets worse. The variables for estimating statistical power usually come from published studies, and published studies are not necessarily reliable sources of true effect sizes because of publication biases. So, non-significant results are less likely to be published, thus distorting the estimates. Taken together, statistical power is a metric that can help guide your decision-making about doing research, but it should not be relied on without critical consideration. There is no single formula to calculate statistical power in all situations and for all analyses. Instead, the formulas are based on many parameters, including the type of analysis, so ANOVA versus regression versus t-test, and the complexity of the analysis model, so a one-way ANOVA versus a three-way ANOVA with all interactions. In the rest of this section, I will focus on one formula to help you build intuition, and then in later sections, I will provide a brief introduction to a free tool for estimating statistical power in a larger variety of analyses. Fortunately, the concepts involved in estimating statistical power are the same for all analyses, so the knowledge you will gain from this chapter will generalize to any other power calculation. Section 17.2.1 Statistical Power of a One-Sample t-test. Here is the formula to calculate the statistical power of a one-sample t-test. Before reading my explanation of the equations below, please take a moment to try to understand equation 17.2 and how that maps onto the dark gray patch labeled 1 minus beta in figure 17.1. Here we have two equations. The first equation is the typical definition for a one-sample t-test. It reads t with df, degrees of freedom, equals the fraction with the numerator being x bar minus h naught, and the denominator is s divided by square root of n. Then we have equation 17.2 for 1 minus beta. So 1 minus beta equals the probability of t, capital T, is less than or equal to minus tau of alpha over 2 plus t that I just defined, lowercase t that I defined in equation 17.1, plus 1 minus the probability of capital T less than or equal to tau of alpha over 2 plus lowercase t. Back to the text. You should recognize equation 17.1 as being the t-value, the distance to the null hypothesis value in the numerator, standard error of the mean in the denominator. In equation 17.2, the tau of alpha over 2 term is the t-value corresponding to the alpha threshold, typically 0.05, with df, degrees of freedom. This is the critical t-value that you learned about in chapter 11. The plus t means that we're shifting the t PDF from being centered at 0 to being centered at t. The capital T is the CDF of the t-distribution. And the 1 minus factor is because we want the probability of t-values to the right of the target value. Now that you've seen this equation, have another look at the distributions in figure 17.1. The HA distribution is the shifted version of the H0 t-PDF. The vertical dashed line at alpha is tau of alpha over 2. And the second additive term in equation 17.2 is the dark shaded region labeled 1 minus beta. The main difference between figure 17.1 and equation 17.2 is that the figure shows only the right tail, whereas the equation includes both tails. Note the implicit assumption that the HA distribution has the same shape as the H0 distribution. True versus estimated power. Equation 17.1 is the estimated statistical power computed from an empirical sample. If you know the population mean and standard deviation, you would use mu and sigma instead of x bar and s. As with all other situations in statistics where population characteristics are unknown and estimated from empirical samples, the estimated power should be a good replacement for the true power if the sample is random and representative. Example. Imagine a study with a sample mean of x bar equals 1, h0 equals 0, s equals 2, and n equals 42. Using these values, tau equals 3.24, and the shifted critical t-values are 1.22 and 5.26. The total area left of 1.22 and right of 5.26, which is the statistical power in this sample, is 1 minus beta equals 0.8854. That's a good amount of power. Below is the Python code to compute the power in this example. Please take a moment to see how this code is a translation of equation 17.2. Here we have some lines of code defining x bar equals 1, std equals 2, n equals 42. Then we have the critical t-values. This is two-tailed, so we have two lines of code. We have variable t crit l for left critical t-value equals stats.t.ppf with inputs 0.05 divided by 2 and n minus 1. And then we have t crit r for the right critical value, that is stats.t.ppf 1 minus 0.05 divided by 2 and n minus 1. Then I define some other variables for the power on the left and the right. So first I have variable t, that's the empirical t-value, that is variable t equals x bar divided by the quantity std divided by square root of n. Then I define power left is stats.t.cdf of t crit plus t, n minus 1. Sorry, t crit l, so the left critical t-value plus the empirical t-value. And then I define the power r, so power on the right side of the distribution equals 1 minus stats.t.cdf with inputs t crit r plus t and n minus 1. Then the total power is simply total power equals power left plus power right. Then I have the corresponding R code. The details of the syntax are slightly different, but the overall idea of the code is exactly the same as with the Python code. Back to the text. Figure 17.2 visualizes the power calculation for the characteristics used in this example. 3 remarks about interpreting this figure. Remark 1. This figure shows the two-tailed power calculation, but the area of the left of minus tau over 2 is too small to be seen. You can modify the code to have a negative x bar to see the HA distribution on the left of the H0 distribution, or use a logarithmic y-axis scaling. Remark 2. the x-axis is t-values, not data values. This means that the width of the distributions are determined by the degrees of freedom, not by the standard deviation of the data. Changing the standard deviations will change the distance between the H0 and the HA distributions, but will not make the HA distribution wider or narrower. Remark 3. The peak of the HA distribution is the observed t-value. The implicit assumption is that if HA were true, and you repeated the experiment many times, the distribution of sample t-values would be centered at the observed t-value. The code to produce this figure is online. I encourage you to spend a few minutes exploring how the sample characteristics impact the graph and the power. This paragraph references figure 17.2, which shows an illustration of statistical power in the simulation. We see two t-distributions, so they look kind of like Gaussian distributions. One is a black line corresponding to the H0 distribution, and then we have a gray dashed line that is shifted to the right, indicating the HA distribution. The x-axis is labeled t-values and goes from -4 up to 6, and the y-axis corresponds to probability values. So we have vertical dotted lines at t equals -2 and +2, and those are labeled minus tau over 2 for t minus 2, and plus tau over 2 for t equals 2. And then we see that the area of the HA distribution, that is to the right of the tau over 2 dashed line, is shaded in gray, and that is labeled as 1 minus beta equals 0.885. Now there is technically a shaded region also to the left of minus tau over 2 in the HA distribution, but it's so small, it's so close to 0 that you don't actually visually see any shading. Back to the text. I wrote out the code to compute power so you can see how the equations are implemented and how that maps onto the visualizations of the distributions. In practice, you can compute statistical power using the stats models library in Python, the PWR library in R, or a software program called GStarPower. I'll introduce these implementations later in the chapter. Section 17.3, How to Increase Statistical Power. Please refer to equations 17.1 and 17.2 in the discussion below. Although those equations are for a one-sample t-test, the concepts explained below are valid for any calculation of statistical power. You will have the opportunity to discover how those factors impact the statistical power in the exercises. In general, higher statistical power is better, and you should try to design your experiment and data processing to maximize statistical power. But power is not the only consideration, and therefore, maximizing power should not come at the expense of other experimental, statistical, and practical considerations. Here are ways to increase statistical power, along with discussions about why each method is not necessarily trivial or even desirable. Method 1. Increase sample size. Power increases with sample size. This is the primary motivation for using large sample sizes. However, power increases proportional to the square root of sample size, so increasing the sample size is beneficial only up to a certain point, after which gathering more data provides little added benefit. Well, how much benefit you gain depends on the effect size, which you will discover in the exercises. In some research studies, increasing sample size is easy, for example, online surveys. In other studies, it is difficult due to the cost or time to collect data. For example, studying post-surgical pain in patients with rare tumors. Method 2. Increase effect size. The larger the effect size, the larger the statistical power. The universe would be very kind to scientists if we could arbitrarily control the effect size in our research. But the universe is a cold and indifferent place, and we cannot decide the effect size in advance. Furthermore, effect sizes are generally getting smaller over time because many large effect size studies have already been done, and therefore modern research is based on searching for more subtle and more nuanced patterns, which means smaller effect sizes. Method 3. Decrease sample variability. Samples with less variability, that is, smaller sample standard deviation, have larger statistical power. To some extent, decreasing sample variability is possible by improving experimental controls, using more accurate measurement equipment, sampling from homogeneous populations, and cleaning data to remove outliers or other non-representative samples. But decreasing sample variability runs the risk of decreasing generalizability. For example, collecting data only from 20-year-old white males enrolled in an economics program at the University of Lyon is likely to reduce sample standard deviation, but it severely limits the generalizability of the findings. Method 4. Decrease the significance threshold. From figure 17.1, you can see that power will increase simply by shifting alpha to the left. However, this comes at a cost because it means increasing the p-value threshold and therefore increasing the risk of type 1 errors. For example, if you set the p-value threshold for statistical significance to be p less than 0.3, then statistical power will be very high, but the probability of a false alarm will be unacceptably high. You can see that there is no foolproof way to increase statistical power. Each strategy for increasing statistical power comes with its own costs or limitations, some of which you can influence while others you cannot. In practice, increasing sample size is the most common way to boost statistical power, and this is why most applications of statistical power calculations focus on estimating appropriate sample sizes. Section 17.4, Estimating a required sample size. Estimating a required sample size is conceptually straightforward. Given expected values of x bar and s, and given a desired level of statistical power 1 minus beta, solve equation 17.2 for n. Unfortunately, inverting the equations is not always so simple. For example, the t distribution is a function of the degrees of freedom parameter, which itself is based on the sample size. Similar story for an F statistic in ANOVAs and regressions, especially in an unbalanced design in which different factors or levels have different sample sizes. Furthermore, there can be numerical issues, for example, rounding errors, with the inversions that reduce the accuracy of the sample size estimate, particularly for values close to 0. Therefore, in practice, the sample size is found through an iterative search. An iterative search works by guessing a starting value of n and computing the power for that sample size. If the sample size produces a statistical power lower than the desired value, the sample size is increased and the calculation is repeated. And the sample size would be decreased if the calculated power was too high. This process of adapting the sample size and recomputing power continues until 1 minus beta is close to the desired statistical power. Footnote: there are some statistical tests that are simple enough to be inverted and solved for n, in which case the sample size can be immediately calculated. The z-test is one example. Back to the text. Examples. Let's assume we expect a sample mean of x bar equals 1 and a sample standard deviation of 1.5, and are testing against the null hypothesis that mu equals 0. If we want to obtain a statistical power of 0.8, we need a dataset with n equals 20. I calculated that using the stats models library. I'll show the code later in this chapter. Now, if the mean is smaller, the required sample size will increase. For example, if x bar is 1/2 instead of 1, then the required sample size is n equals 73. In other words, the required sample size has nearly quadrupled when the mean was halved. And because the calculation is based on the t-value, you actually get the same required sample size by doubling the standard deviation instead of halving the sample mean. If we use the original x bar equals 1 but want to have a power of 0.9, then we need n equals 26 data points. I hope these results are all intuitive. Smaller effects and higher power require more data. You will have several opportunities to explore these calculations yourself in the exercises. Section 17.4.1, where do the expected values come from? The desired level of statistical power can be set to 0.8. This value is arbitrary, but it is widely accepted in many fields. But power calculations also require knowing sample characteristics such as the mean and standard deviation. How do you calculate the required sample size before collecting data if you need to know the sample characteristics before getting the data? It seems like this would require a time traveler from the future to tell you the sample characteristics so that you can collect a sample so that the time traveler would know the characteristics to go back in time and tell you. It all gets really confusing. The answer is that you cannot know the sample characteristics in advance. You must guess reasonable values. So how do you guess reasonable values? There are two ways. 1. Run a pilot study. As I explained in Chapter 2, a pilot study is a small-scale version of your study that you use to check for confounds in your experiment or equipment problems. If the pilot data are sufficiently similar to the main experiment data, you can use the pilot sample characteristics in the power calculations. On the other hand, you may not want to use these data if you modified the experiment or equipment after discovering problems in the pilot study, or if the pilot sample size is too small to provide reliable estimates of the mean and standard deviation. Number 2, use values from published studies. Find publications that used similar experimental techniques and data analyses as what you plan on having. If possible, you can use your own previous studies because the equipment and experimental protocols are likely to be the same or similar. The problem with this approach is that the published literature may not provide an accurate estimate of the sample characteristics considering publication biases. People are more likely to publish statistically significant effects than non-significant effects, and this increases the risk that you will overestimate the statistical power and therefore underestimate the required sample size. You can see that there are no great options here. Indeed, estimating an appropriate sample size is a bit of an art. Another source of uncertainty is that you may need to exclude data due to outliers or equipment malfunctions. In these cases, it's a good idea to pad the sample size calculation. For example, let's say that based on your experience, you can expect that 10% of your dataset will be rejected due to outliers or technical problems. Therefore, if a sample size calculation suggests that you need n equals 100, you can plan to collect n equals 110. Section 17.5, Computing Statistical Power in Practice. I hope you find the code I presented earlier in this chapter to be enlightening. In practice, there are several reasons not to use your own code to compute power and estimate sample size, but instead to use libraries and software developed by professionals. The main reason is that the calculations are complicated and tedious for all but the simplest statistical tests. There are many statistical power calculators that you can find with some web searching. In this section, I will introduce you to 3 calculators. I chose to highlight these 3 for practical reasons. I do not imply that any other calculators are inaccurate, less useful, or should be avoided. Section 17.5.1, Using Stats Models in Python. The Stats Models library comes with functions for computing power and sample size. Here I will show an implementation for the one-sample t-test, and I will guide you through additional applications in the exercises. The statistical power calculations are in a module of stats models called stats.power. So we begin by importing that module and abbreviating it as SNP. So here we have a line of Python code. It reads import statsmodels.stats.power as SMP. Computing power. The code below shows how to compute the statistical power for a one-sample t-test. The parameters are the same as the ones I used in the manual implementation earlier in this chapter. The code below uses the power method on the t-test power object to compute statistical power based on sample characteristics. Here we have some Python code. I define variable xbar equals 1, std equals 2, and sample size equals 42. Then there is a line where I define effect size equals x bar divided by std, and then the actual power calculation is done in the following line. I compute variable power sm equals smp.ttestpower.power with inputs effect size equals variable effect size, n-obs equals sample size, alpha equals 0.05, and alternative equals two-tailed. The variable power sm is 1 minus beta. With these parameter values, the power is 0.8856. That is slightly different from the value of 0.8854 that I obtained with the manual implementation shown earlier in this chapter. Such a tiny difference is negligible and can be attributed to minor differences in implementation and rounding. Notice that the input variables that smp.ttestpower uses are slightly different from the equations I presented. In particular, t-test power takes the effect size and not the t-value. As you will recall from chapter 11, the difference between those quantities is that the effect size has only the standard deviation in the denominator without scaling by the square root of n. Calculating sample size. You can compute the required sample size for a given desired statistical power using the solve power method. Many of the inputs are the same as for the power calculation above, except that there is no input for n-obs, and the goal of this function is therefore to calculate the unknown number of observations. So here I have some Python code. I define variables power equals 0.8, x bar equals 1, std equals 1.5. And then again, I define the effect size as variable effect size equals x bar divided by std. And then finally, we have the code to compute the sample size that reads variable sample size equals smp.ttestpower.solvePower with inputs effect size equals effect size, alpha equals 0.05, power equals power, and alternative equals two-sided. This is the code that I used to calculate that the sample size should be 20 in the example sample size calculation discussed in the previous section. The statsmodels.stats.power module comes with functions for one sample and independent t-tests. And remember that a paired samples t-test is the same as a one sample t-test on different values. and also for a one-factor balanced ANOVA, among several other tests that are less commonly used in statistics. The advantage of using the stats models library is that it is easy to integrate into your Python workflow. However, if you want to calculate power and sample size for a more diversified range of statistical tests, you should consider using the dedicated software package GStarPower. I will discuss that in a moment. Section 17.5.2 Using PWR Power in R. The Power library, spelled PWR, comes with functions for computing power and sample size. Here I will show an implementation for the one-sample t-test, and I will guide you through additional applications in the exercises. We begin by installing, if you haven't already installed it, and then importing the Power library. So here we have 2 lines of R code. Install that packages Power, and then we call library Power. Computing power. The code below shows how to compute the statistical power for a one-sample t-test. The parameters are the same as the ones I used in the manual implementation earlier in the chapter. Here I define variables. X bar is 1, std is 2, samp size is 42, and alpha is 0.05. Then I compute the effect size as variable effect size is x bar divided by std. And then there's the line to compute the statistical power, and that reads variable power sm is pwr.t.test with inputs d equals effect size, n equals samp size, type equals 1.sample, sig.level equals alpha, and alternative equals 2.cited. That variable power sm is 1 minus beta. With these variables, the power is 0.8856. That's actually the same as with the Python implementation. And that is slightly different from the value of 0.8854 that I obtained with the manual implementation shown earlier in this chapter. Such a tiny difference is negligible and can be attributed to minor differences in implementation and rounding. Notice that the input variables that power.t.test uses are slightly different from the equations I presented. In particular, power.t.test takes the effect size and not the t-value. As you will recall from chapter 11, the difference between those quantities is that the effect size has only the standard deviation in the denominator without scaling by the square root of n. Computing sample size. You can compute the required sample size for a given desired statistical power using the same pwr.t.test function. Many of the inputs are the same as for the power calculation above, except that there is no input for n, so the sample size. And the goal of the function is to calculate the unknown number of observations. Here we have some R code. I define variables power is 0.8, x bar is 1, and std is 1.5. And then again, I define the effect size as variable effect size is x bar over std. And finally, we have the line to compute the sample size. And here I define variable sample size calc is pwr.t.test with inputs d equals effect size, power equals power, sig.level equals 0.05, type equals 1.sample, and alternative equals 2.cited. Notice the logic of using pwr.t.test. In the first example, I excluded the power input, and the function returned the statistical power. In the second example, I included the desired power and excluded the n input, and the function returned the required sample size. The PWR library comes with functions for one sample and independent t-tests. And remember that a paired samples t-test is the same as the one-sample t-test on difference values, and also functions for correlation, ANOVA, among several other tests. The advantage of using the PWR library is that it is easy to integrate into your R workflow. However, if you want to calculate power and sample size for a more diversified range of statistical tests, you should consider using the dedicated software package gstar.power. Section 17.5.3 Using GStar Power Software. Disclosure: I have no affiliation with the software or with the developers of GStar Power. It is free, widely used, and therefore widely recommended. This section is not meant as a complete guide or even an in-depth tutorial on using the software, but it is an easy program to use, and you can educate yourself on the software if you feel it would be useful for you. The main website for this software can be viewed directly by typing a really long URL into your browser. Honestly, though, it's easier to find the website by searching the web for GStar Power. Here in the book, I list this really long German URL, which I'm not going to repeat here. The software is fast and easy to install and will look like Figure 17.3 when you open it. Figure 17.3 shows a screenshot of the GStar Power window when you open the program. There's not much I can describe about this, you just have to use the software. Figure 17.4 shows an example power calculation for a repeated measures ANOVA. I know the font is small, it's a screenshot of how the software looks on my laptop screen. My main goal here is to make you aware of this software so you can explore it on your own. This paragraph references Figure 17.4, which shows the GStar Power window when calculating required sample size for a repeated measures ANOVA. This is just a screenshot of the software. The software is convenient to use because it allows you to select different types of analyses, enter different metrics such as the effect size, the number of observations, the number of groups, and so on in windows, and it displays nice graphs that illustrate the beta and alpha regions. Back to the text. There are many options available through GStar Power that provide detailed insights when planning your study. You can find a full manual and a short tutorial of GStar Power on the main software website, and you can also find video tutorials on YouTube. As of this writing, there are no tutorials on TikTok. Perhaps that's a good opportunity for an enterprising statistician influencer. Section 17.6 A priori power versus post hoc power. Broadly speaking, there are two ways of performing a statistical power analysis. Before the study begins, this is called a priori power, and after you finish your statistical analysis, that's called post hoc power. A priori power. This is done before you begin data collection, and it involves estimating an appropriate sample size based on the effect sizes and standard deviations from published studies or from a pilot study that you performed. This approach is common and widely accepted. Indeed, an a priori sample size estimate is often required in funding applications and research ethics board approvals. But it is far from perfect for several reasons. Reason 1. There are publication biases that prevent an accurate estimate of true effect sizes based on the published literature, as mentioned earlier and discussed more in the next section. Reason 2. Different analyses within one dataset will have different effect sizes. Most modern datasets provide myriad opportunities for hypothesis testing and data mining, and different analyses may have different statistical power and therefore require different sample sizes. Reason 3. There is no guarantee that the statistical characteristics you use in your power calculations will be replicated in your sample. Your sample might have different means and standard deviations due to sampling variability, different measurement equipment or experimental techniques, different hypotheses, and so on. Reason 4. There are real-world constraints on how much data can be collected. Perhaps your experiment is expensive and time-consuming to perform, and you have limited time to complete the study. Perhaps you simply do not have the resources to collect the sample size required for 90% power, so instead you opt for a sample size corresponding to 70% power. This may not be ideal, but we do the best we can in lieu of an ideal world. Post hoc power. Post hoc power is sometimes called achieved power, and this is done after you have finished your data collection, cleaning, and final statistical analyses. The idea is to compute the empirical 1 minus beta based on the sample mean, sample variance, and sample size in your study. Because post hoc statistical power is entirely determined by the sample descriptive statistics, it does not provide unique information that is not already reported in the results of the study, but it does provide the information in a way that can help your audience contextualize the statistical characteristics of the findings. One example is to report a required sample size for a given power level. Imagine the following statement in a research paper, quote, "Our post hoc statistical power was 0.94 with a sample size of n equals 150. Obtaining a statistical power of 0.8 would have required only n equals 85, end quote. Such a statement could be useful for other research groups who might have difficulties obtaining large sample sizes. Of course, this calculation can be performed by another researcher based on your publication, but you're a super duper nice person if you do it for them. Section 17.7, Assumptions of Power Calculations. Because each formula to calculate statistical power is based on the null and alternative hypothesis distributions for each statistic, the assumptions of power calculations are the same as the assumptions for the statistical analysis for which the power is calculated. As you know, most of those assumptions involve normal distributions, random and independent sampling, and homogeneity of variance. When your data violate those assumptions, you can estimate power empirically using data simulations. The idea is that you do not have a theoretical alternative hypothesis distribution, so you simulate many data sets where HA is true in order to obtain an empirical HA distribution. If the simulated data match the assumptions of the power analysis, then the empirical and analytical HA power calculations will be nearly identical. However, when your data violate the assumptions of the analytic power analysis, the empirical and analytic power calculations will differ. I will guide you through the motivation and implementation of empirical power calculations in exercises 7 and 8. Section 17.8, Exercises. The exercises for this chapter are great. They're super fun and informative. I encourage you to check out my YouTube channel where I have video walkthroughs of the exercises and their solutions. End of chapter 17.